Linwei Wang, who's going to be speaking to us from Rochester, who's going to be speaking to us about physics-integrated hybrid models in cardiac digital twins. Thank you.
Well, hello everyone. It's great to be here. It's been a very stimulating event, and I'm very excited to be here today to talk about some of really recent work in what we call hybrid modeling. And as you will see in the slides, much of the slide actually doesn't really have to do with the heart, and that is really the reason I'm here, to bounce this idea of the experts here and to see if there's an opportunity for synergy. So I think there has been a couple of very excellent talks earlier, about physics-informed neural networks, PINs, and surrogate model in general. So what's the difference in what we call hybrid model? So let's say we have a magnetic model, the simulation model, and then we have a neural network. So usually in PINs, or in physics-informed neural networks, what we want to do is to have these two models describe the same thing, right? So we want this neural network to be solving the PDEs that we are interested in, or in a more general sense, if it's a surrogate model, then we want the neural network to describe the same thing that this physics-based model is describing. And if it's the forward PIN, then the physics PDE is constraining the neural network. And if it's inverse, then they're sort of constraining each other. In hybrid model, what we call hybrid model, it's sort of for a different purpose. So in hybrid model, it's in a setting where you are really certain about some part of the physics, and you really don't think you need to learn it with a neural network. So you would like to keep that part of the model. And then you want to focus on your neural network in learning the part that your model is not explaining to the data. So it's really sort of a way of bridging what your physics is describing and what data is describing. So in this hybrid model, these two models together describe the data you're observing, and they're sort of complementing each other. So this hybrid model, also called gray box modeling, has been getting a lot of interest in machine learning community in the last couple of years. In the earlier effort, usually we see what we call residual modeling. So in that sense, the learning of the neural network doesn't really see the model itself. It sees the output of the model, and you're trying to learn the residual, trying to make up the difference. The more recent set of works, including I think one of the works Martha mentioned in her talk yesterday, is trying to going for a more tighter integration between these two models. So just to put in a more concrete setting. So just imagine we are talking about a pendulum. It's moving over time. And let's say we know that the first two terms in this PDE really describes how the pendulum will move in a very idealized system when there's no friction or anything. The third term describing what friction does, damping. And then last term describing the external force that gets applied to the pendulum. So now let's say you're presented with some data that's describing some pendulum, how it moves. And you go, okay, I think I know the first two terms really well, and I think because it's a pendulum, it will have to follow that part. So you want to keep that physics component of the equation. Well, you let it to have a parameter omega there that can be learned, that can be inferred, but the equation is there. And then you say, okay, for the rest of terms, I'm really unsure because I'm not certain about the exact condition this data is observed. So I'm going to model it with a neural network. So this neural network can also have some abstract latent variables. Because it is abstract, it's not going to have physical meaning that's corresponding to the rest of the parameters that are controlling this equation. But if it's well learned, it should have a good correlation with this parameter because it should be explaining the main variables in your unknown equation that sort of affect your data. So this is how a hybrid model will look like. You have a hybrid model that has some physics component, has some neural network component. They each have parameters that you can infer from data. So I want to sort of emphasize again, on the physics component, you will have parameter that's physically meaningful. And then on the neural component, you still have some abstract parameters. These parameters can be inferred from data and affect the weight of the neural network, but they are abstract because they are learned from neural networks. But if they're well identified, they should have correlations to the true variables that's affecting your data. So I think this overall network is sort of intuitive. It sounds simple. So what are the challenges that people are addressing now? So the first question is really identifiability. So the question is, we already know in this community that even if you only have that physics component, and if you want to identify the parameters, it's already hard enough, right? And now you want to identify the parameters together with some additional component that's unknown. It's definitely going to be harder. So in the last couple of years, there have been works that are trying to address this identification issue. Most of the work has been focusing on the particular issue. If you think about these two models, so a physics component that's prescribed equation and a neural network. And together, you're trying to fit this whole thing to the data. So if you don't deal with carefully, it's very likely your model might just decide to ignore the physics part and try to fit the whole thing with your neural component. So that's what this first book means. So there's been solutions proposed to try to address this issue. Mainly, the idea is try to constrain the expressiveness of the neural component to make sure its output is, for instance, to put an L2 norm minimization on the output to make sure it doesn't just try to describe the whole thing. But there's actually a more fundamental challenge we're looking at here. That's what is known as unidentifiability of deep generative models. So what does that mean? Let's just think about a variational autoencoder, because it was mentioned a lot, I think, yesterday. So if we think about variational autoencoder, that's how we describe our data. So we have, usually if let's say this is what we are observing, and then this C is the latent variable. So when we do a variational autoencoder, you have a decoder that's supposed to be describing the likelihood of how this latent variable is giving rise to your data. And then you have some prior distribution you have on your latent variable. And then you have this encoder of the variational autoencoder that's supposed to give you the posterior distribution of your latent variable. So the unidentifiability of generative model is already established. If you're interested, you can check the paper for theoretical proof. But the idea is simple. The fact is just, you can find transformations that can change the value of your Z. For instance, imagine you have such transformations in your encoder that can change the value of your latent variable without changing its distribution. And then this decoder that you are learning can sort of absorb that transformation, if that makes sense. So in the end, because the way we are fitting the model is only the data, we can't see the latent variable. So as a result, despite those transformations that happens in the encoder and decoder, your fit will be the same. So as a result, even though you are fitting the data very well, your Z, your posterior of Z, and your likelihood function is really not identified. So that's very well established in the in the deep generative modeling literature, and this will apply to a hybrid model. So if you think about a hybrid model, when this thing becomes hybrid, the physics component will be less affected by that because your decoder has a physical meaning, but the neural component will have the same issue. But this has never established when we're dealing with hybrid modeling. And the good news is, in the literature of nonlinear independent component analysis, there's actually a way people have proposed that you can use to establish identifiable generative models. And the way to do this is actually simple. Instead of, we call this a non-conditional unconditional pry. So if you can establish a conditional generative model where your latent variable is conditioned on something, this U is called the auxiliary variable. If you can construct a conditional generative model that's conditional independent to each other given this variable, then your model becomes identifiable. The problem with existing solution is this U has to be observed. So typically in literature, when people deal with this takes form like the label of your classification. So if we take a step back and think about the type of problem we are trying to address, like you're trying to model a physical system, this type of label is not very obvious. So in our recent work, we are proposing meta-learning as a solution to overcome this identifiability. So I'm not going to start by introducing meta-learning. I'm going to introducing why is address identifiability and come back to meta-learning. So the idea is simple, like I said. What we need to do is to create a generative model that's conditioned on something. So in this equation, this is your generative model that we just described. That describes how your data is produced by a combination of physics and neural component. So the physics component, we still let it to be just a simple unconditional pry. For the neural component, we let it condition on some so-called context sample. So context sample is a sample if you have let's say, imagine you have a sample X that you're trying to fit. Context sample is some other samples that you know come from the same system, share the same latent parameters of this current sample, but it's different samples. So if you think about hard modeling, you can think about different recordings of the same patient under the same at that one moment. And then this is really in the end what we are doing is that these conditional pry, these latent variable from neural component, we are modeling it as condition on some context sample. So in the end, it's really just, for instance, you can model it as some exponential family of distribution, and you say its parameters of this distribution is characterized by some function like this. And this function you can learn from neural network. So you have a neural network encoder applied to individual context samples, and then you can aggregate over this whole set of samples, and that's your latent variable. So we have the identifiability proof in our recent work, but I want to offer a much sort of intuitive explanation to this whole thing. So if a generative model or hybrid model is unconditional, then if you think about a variational autoencoder setting, what you will do is you have an encoder to infer latent variable and then reconstruct it, right? That's a common way to do it. So what does this mean is when you're training this model, what you do is take a sample, optimize, and reconstruct it, and that's your training loss. And what this unidentifiability theorem shows is just saying when you reconstruct something well, it doesn't mean things are identified. And I think this will resonate with everyone in this, in this room. Because when we're modeling, I think I have heard a lot of talks, especially I think this morning Gernot talk also mentioned that we emphasize predictive capability, right? Just because you had a very good fit or reconstruction, that does not necessarily mean things are identified. The true evidence for identifiability is you can take this identified model and go predict something else, right? So this is exactly what this meta formulation means. In meta formulation, you are identifying your latent variable from some example that come from the same system with this thing you're trying to generate, but it's not the same data. So this is basically, if we're thinking about this, take a step back to the cardiac modeling. This will be trying to optimize a parameter, try to fit a given observation, versus this will be take the optimized parameter and have it predict something else that share the same parameter but in a different condition. So basically, this is what meta learning is about. Meta learning is about you train a neural network or train the model not to just do reconstruction, but train it to identify its parameter from some data and use it to predict for some other data that share the same parameter of this sample, but not the same. So in terms of meta training, that's what we do. You have, assuming you have a couple of systems in your training data, each of them have different samples. So you take a small context set to identify the latent variable and then ask that identified model to generate the rest of the samples. And you do that over many different shifts. So again, the key is really reconstruction is not a good indication of identification. We want to do prediction, and you can train a neural network that way. So our experiments, as I mentioned, as this stage, our experiments are done on benchmark physical systems that's commonly used in this literature. So these are the type examples. So the pendulum is the example I already give. And this is sort of another system where to test this, we'll just take the first component as a physics component and let the model learn the rest. So these two examples are basically the neural network is supposed to be learning some additive errors to the system. And then this is a double pendulum example where the physics component is modeled as such, and then the neural component is trying to make up for the rest. And this is a multiplicative error. And then we also have some real data as from a video of double pendulum. So in that state, you don't know what's the true generation equation, but we use this as the physics component. So for matrix, for the two latent parameters, for the viscous parameter is simple. We look at MSE because they have physical meanings. For the neural part of the parameter, because like I said, they are abstract, so you can do MSE, but you can look at its mean correlation coefficients with the true parameters in the missing part of the equation. So if it's well identified, you expect to see a high correlation. And then we also look at this too. For us, it's very interesting. So like I mentioned, to just again stress this difference of reconstructing a given signal versus being able to use it to generate for new signals. So we also look at these two things. So if you look at this, so this last one is the model, we were proposing adding a meta component to it. So as you can see, for predicting the viscous component, for identifying the viscous parameter of the component, I think our model does pretty well. So again, that's sort of agree with the theorem that the viscous part of the model doesn't really suffer from identifiability issue. But if you look at the neural component, you will see that when you add meta learning, you have a much higher mean correlation coefficient with the actual parameter that's missing in the equation. So that means for the neural component in the hybrid model, meta learning is really important in ensuring you're identifying the right thing. And then if you look at the signal, this should be Z. Again, if you're looking at reconstruction, you will see all this model is doing really well in fitting the given data. But if you ask it to take the identified model and then use it to predict for other samples that share the same parameter but with different initial condition, for instance, they mostly doesn't do very well. And it's very important for this meta component to make sure it can actually do it. So I think this, again, stressing the importance of, do you look at reconstruction fit or do you look at its ability to predict? And then in real data, again, it's the same idea. Because in real data, we don't really know what's these true parameters because we don't know the actual model. But if you look at the same thing, reconstructing is easy for all models. But to be able to take the identifier model to do prediction, you need a meta component to make sure it's actually identifiable. And this is just some examples, visual examples of different systems, reconstruction versus generation results, individual samples of the variables you're trying to fit. So again, the same idea. For the model to be able to predict after it's being identified, the meta component is really important. So I think I'm very short on time, so I'm gonna just skip around before real quick. So the current status of this type of modeling, right now, everything I said, all the existing models assume that these hybrid models output are fully observed. So what does that mean? Let's just come back to a pendulum example. So in all the works that existing, if we're trying to model this, it's assuming this state variable, this position, angular position is fully observed. So again, if you think about, let's just say in the heart, that will be, if you're trying to model action potential, for instance, this will have to assume your action potential is fully observed, which is not very commonly available. So can we do this by, instead of assuming this angle of the pendulum is observed, can we just directly infer it from a sequence of images, right? So up until now, there's only one existing work that does this, and there's no really discussion of identifiability. So in the framework we are establishing, luckily, to expand it to accommodate this is really easy. It's just, in both the encoding and decoding layer, we are expanding all the way to observation instead of the direct output of the hybrid model. So the hybrid model become a latent model. We actually have done a lot of experiments on the same type of system I just described to show that it works. But we submitted this to one of the machine learning conferences, and we are asked to prove theoretically again. So we're currently working on the theoretical proof of both, not only the parameter that we're showing is identifiable, but the latent variable, the things like the angular position, everything's identifiable over time. But empirical result is very strong. We're comparing this to all these existing models to do this latent type of model in the latent dynamic model in the latent space. with fully neural models, with some physics prime, and with just a completely white box model in the latent space. And the result is pretty strong. But yes, we need to provide theoretical proof at this point. I'm gonna skip through all of this. We've done that also. Actually, we have some recent work that we just get completed on doing this on dynamic PET reconstruction. I think, well, I just want to mention this real quick. So we are very interested in applying this to cardiac systems. In my group, we don't do modeling ourselves, so we have very limited capability in here. So we are doing some very, very, very toy examples to just show that it works. For instance, one example we do is like this. We take the Elif Penfield model, and we say we'll keep this component as the known physics. And we want to see if the neural network will be able to pick up this component. And then this is a result that we're showing. So the orange curve is when you take off that last component of the Elif Penfield model, then there's no more repolarization. And then I think the blue curve is the actual model, and then the green one is what's learned by the hybrid model. And we're also doing something like, we're also trying things like, for instance, we take the physics component to be the Iconal model, and then we want the neural network to then bridge from the Iconal model to the, in here, the action Elif Penfield model. And again, we have some very initial results to try to show, this hybrid approach will be better than if you just do completely neural network or completely physics-based. But I will stop here, so we can have some time for discussion. But really, the main reason I'm here is that we are pretty excited about this framework that we think is theoretically proven, and also we have pretty good results on those benchmark systems you saw. And we're here to hear your feedback. Like, is this even useful? Is this even of interest? And is there interest in cloud? Yep. Thank you.
So, a couple of quick questions. Yeah.
Nice talk. So meta-learning effect will be two sources of data, sort of main data for model calibration and identification, and then sort of the data related to the meta component. How informative do these data have to be? Is my intuition right that you can get away with low quantity, high noise data, that only what you need is enough information to break symmetries, so that you can then deal with the identifiability problem, so that the quality of the metadata doesn't need to be so high that...
Yeah, so when this happens, it's really, just a set of data. And then during training, for the data coming from the same, if we know it's coming from the same system, we just randomly split into a very small, so I forgot to mention the K short context data, the K is usually between 1 to 5. So very small set of data is left out for the identification. And then the rest, it is supposed to be then testing how this identified model works on it.
Yeah, I would assume that intuitively want to sacrifice as little data as possible, but my intuition would be to get away with
But we don't really, so you shovel through that process during training. So, let's say in this system, I have 100 data points. So in this epoch, I take 5 out as context, and the rest is to generate the loss. And then in the next epoch, I will take another 5 out. So yeah, so you just cycle through all of the data sets in the end. But the important thing is, I think, is you don't do reconstruction. The model has to able to identify this model to predict for something else. Yeah.
Time for one quick question before we get set up. Alex?
Yeah, it's a bit of a follow-up to the previous one. Does the theory tell you the structure, this contextual sample is like measuring something else, right? Does the theory tell you the properties that something else has to have?
The what?
The properties that something else you're measuring.
They have to be the same, coming from the same system.
Process.
Yeah.
But
But
I suspect not everything that comes from the same process will sort out the problem of identifiability, right?
Yeah, so I think if you go to practical issues when there's errors trying to figure out if things are coming from the same system, then I think there will be additional challenges. But the theory does tell us how many systems you need in order to identify. Like if you have these many parameters, how many different systems you need to observe in order to identify.
That's great. If we could thank Linwei again. Thank you.